Voyager 1 is listening. It is the most distant, human-made object in the universe. It has been moving away from Earth for over 48 years. It is currently more than 24 billion kilometers from the planet that built it, and it is still, every single day, transmitting back the sound of the space it is moving through. We did not expect this. When Voyager 1 was launched in September 1977, the engineers who designed its instruments were not thinking about what would happen 48 years later. They were thinking about Jupiter and Saturn, the two planets the spacecraft was scheduled to visit. The instruments were designed for those flybys. The mission was, at most, supposed to last a decade. Voyager 1 finished its planetary mission in 1980. Then it kept going. NASA renamed the mission. The spacecraft passed the orbit of Pluto in 1989. It crossed the termination shock, the boundary where the solar wind first slows down, in December 2004. It took another 8 years to reach the next boundary. In August 2012, Voyager 1 became the first human-built object to leave the heliosphere. The heliosphere is the bubble of plasma blown out by the sun. Inside it, everything is dominated by particles flowing from our star. Outside it, you are in interstellar space, the medium between the stars, a region shaped by the slow drift of dust and plasma from supernova explosions, ancient stars, and processes that have been running for billions of years before the sun existed. Voyager 1 crossed the line, and it kept reporting. This is where the story actually starts. The instrument that turned Voyager 1 into a listening post in interstellar space was not designed to listen to interstellar space. It was designed to study planetary magnetospheres. It is called the Plasma Wave Subsystem, or PWS. Its lead designer was a physicist at the University of Iowa named Don Gurnett, who spent his career building instruments that could detect electromagnetic oscillations in plasma, the kind of waves that ripple through the gas surrounding planets when charged particles interact with magnetic fields. The PWS was meant to do its job at Jupiter, Saturn, and during the encounters at Uranus and Neptune that Voyager 2 would later make. After those encounters, the instrument was supposed to go quiet. There was no plan for what it might detect light years from any planet. Instead, the instrument refused to die. It has now been operating through the deep cold of interstellar space for over a decade past its design assumptions. Its power source, a radioisotope thermoelectric generator, is fading by about 4 watts every year, and the spacecraft has been progressively shutting down instruments to keep the rest alive. The PWS is still on. The data it sends home is faint, slow, and arrives after a 22-hour radio delay each direction. But it is real, and it is showing us something we did not know was possible to measure. In May 2013, the PWS confirmed what NASA had suspected the previous summer. The plasma density around Voyager 1 had jumped sharply. The spacecraft was no longer surrounded by solar wind. It was surrounded by interstellar medium, the diffuse plasma that fills the galaxy between stars. The transition was not subtle. The plasma waves Voyager 1 detected after August 2012 had a fundamentally different character. The sun was not driving them anymore. Something else was. For 4 years, NASA's interpretation was that the plasma waves Voyager 1 detected in interstellar space were caused by sporadic outbursts, coronal mass ejections from the sun that travelled outward, eventually reaching Voyager 1 and disturbing the local plasma. Each event would produce a few weeks of detectable signal, then go quiet. In between, the instrument detected almost nothing. Almost nothing. In October 2017, a graduate student at Cornell University named Stella Ocker began looking more carefully at the data between the burst events. What she found after years of analysis was published in Nature Astronomy in May 2021. The interstellar plasma was not silent. It was producing a faint, persistent, narrowband emission at a frequency of about 3 kHz. The signal was extraordinarily weak, nearly at the noise floor of the instrument, and it had been hiding in plain sight, dismissed as background for years. It was not background. Voyager 1 was hearing the interstellar medium itself. The plasma between the stars, drifting slowly, oscillating at a fundamental frequency that depends on the local electron density. For the first time, a piece of human technology was directly measuring the sound of the space outside our cosmic neighborhood. If you take the data Voyager 1 transmits, shift it into the audible range and play it back, what you hear is a thin, steady tone. Almost a hum. It is the closest thing to silence that an active environment can produce, and it has been there the whole time. The discovery has consequences. The interstellar plasma that surrounds Voyager 1 turns out to be more turbulent than the standard models predicted. The hum's frequency varies slightly across time and position, which means the medium is denser in some places than others, and the density is changing on scales of years. Either there are structures in the interstellar plasma that we did not expect, or the heliopause itself is leaking, letting solar wind out into a region that was supposed to be cleanly separated from the sun's influence. Both possibilities matter. If the interstellar medium is structured at small scales, our entire framework for understanding how galaxies are filled with plasma needs updating. If the heliopause is porous, then the boundary that protects the solar system from the worst of cosmic radiation is not as solid as we thought, and the dose of radiation that interstellar travelers, human or otherwise, would receive could be different from what models predict. Either way, Voyager 1 is the only instrument we have ever built that can answer the question. It is also the only instrument we will have for a long time. The next spacecraft engineered to study the interstellar medium directly is the Interstellar Mapping and Acceleration Probe, called IMAP. It is scheduled to launch in 2025 and will operate from the L1 Lagrange point, about 1.5 million kilometers from Earth. It will measure interstellar particles that drift into the solar system, but it will not be in interstellar space itself. It cannot replicate what Voyager 1 is doing. NASA has discussed concept missions for a true interstellar probe, a spacecraft that would launch in the 2030s or 2040s, accelerate to higher speeds than Voyager, and reach the heliopause within decades instead of half a century. None of these missions are currently funded. None will be sending back data within Voyager 1's remaining lifespan. Voyager 1 is the only listening post we have, and Voyager 1 is dying. The radioisotope thermoelectric generator on board has been losing power continuously since the spacecraft was launched. Plutonium-238 decays at a fixed rate, and that decay is what powers Voyager 1's electronics. By 2026, the spacecraft has roughly 4 years of operational margin left, and possibly fewer. NASA has been turning off instruments one by one. The Cosmic Rays Subsystem Science instrument was shut down in February 2025. The low-energy charged particle instrument is scheduled for shutdown later in 2026. Engineers are managing the spacecraft like a patient on hospice, keeping the most valuable instruments running for as long as possible, sacrificing the others to extend the life of the ones we cannot replace. The plasma wave subsystem is on the Keep Alive list. There has also been a closer call. In November 2023, Voyager 1 began transmitting unintelligible data, pages of binary code, with no recognizable pattern. The flight data system, the computer that packages the spacecraft's measurements for transmission home, had partially failed. After 5 months of diagnosis from a team of engineers, some of whom came out of retirement to help, NASA determined that a single chip in the FDS memory had stopped working. They worked around it by relocating the affected code to other parts of the memory. Voyager 1 came back online in April 2024. It will not come back online next time. Sometime between 2027 and 2030, depending on power availability and component reliability, Voyager 1 will stop transmitting. It will continue to drift through interstellar space at about 17 kilometers per second, but it will be silent. The instrument that has been listening to the hum of the local interstellar medium will go dark, and the hum will continue, unobserved, the way it has been unobserved for the entirety of the human story before 2017. We will not get this data again for decades, possibly longer. When Voyager 1 stops transmitting, the most extreme observational frontier we have ever extended into the universe will close. We will still be able to see deep space through telescopes, of course. We will still be able to measure cosmic rays in Earth's vicinity, study the sun, model interstellar processes from a distance. But the direct connection, the actual physical instrument floating in the medium it is reporting on, will end. What is striking about all of this is how accidental it is. The PWS was not built to detect the interstellar hum. The mission was not designed to last 48 years. The data hiding the persistent emission was almost dismissed as noise. The graduate student who found it was looking at archives, not making real-time discoveries. Every step of the chain that produced one of the most important measurements of the past decade was a coincidence, a leftover, a near miss. We built a probe to look at Jupiter and Saturn. We pointed it outward. It kept working. Decades later, somebody noticed it had been listening to the sound of the galaxy the entire time. That is the kind of result you cannot plan for. It is the kind of result that emerges only when you keep the lights on long after the original mission is over. Voyager 1 will fall silent in the next handful of years. It will continue moving outward at about 17 kilometers per second. It will not approach another star for roughly 40,000 years, when it will pass within about 1.6 light-years of Gliese 445, an unremarkable star in the constellation Camelopardalis. By then, no one alive today will be listening, even if a transmission were possible. The hum will keep going. The interstellar medium is not affected by whether anyone is observing it. The plasma between the stars will continue to oscillate at its quiet 3 kilohertz tone billions of years into the future, the way it has been doing since long before our species could hear anything at all. We managed to listen for about a decade. We managed to find out in that brief listening window that the universe outside our solar system has a sound, that the sound has structure, that the bubble around our sun may be more porous than we believed, that the medium between the stars is not as quiet or as featureless as our models had assumed. A piece of 1977 hardware did all of that. while sliding through cosmic dark at temperatures and distances that would have killed any modern instrument we tried to substitute for it. And in a few years, it will go quiet, and we will lose the only direct ear we ever had on what is out there. The next time a human-made object reaches that distance, the people watching the data come in will be different people on a different Earth, hearing a different version of the same hum. If they are listening at all, thanks for watching, and I'll see you in the next one.